in this one, the main important is here. So that is nucleophilic substitution. So this is very important for all entrance examination point of view, advanced examination point of view and NEET examination point of view. This is very important topic. Actually, before going to discuss nucleophilic substitution reaction, here we need some basic terms. So nucleophilic substitution reaction చదివే ముందు మనకి కొన్ని basic terms కావాలి. ఆ basic terms గురించి కూడా డిస్కస్ చేద్దాము. First of all, so here we need the definition of nucleophile. Nucleophile అంటే ఏంటి, దాని గురించి మనకు తెలుసుకోవాలి. So first of all, that is nucleophile. The species which attacks where the electron density is less is called nucleophile. Nucleophile అనగా ఎక్కడైతే ఎలక్ట్రాన్ సాంద్రత తక్కువగా ఉంటుందో అక్కడ అటాక్ అయ్యేదాన్ని న్యూక్లియోఫైల్ అంటారు. Nucleophile, the species which attacks where the electron density is more. So now actually the nucleophile is a high electron density species. It is a high electron or electron density species, high electron density species. That means it is an electron rich species. It is an electron rich species. So it acts as a Lewis base. That means it acts as a electron pair donor. Actually here nucleophiles are these nucleophiles are classified into two types. న్యూక్లియోఫైల్లను రెండు రకాలుగా విభజించడం జరిగినది. ఒకటి చార్జ్డ్ న్యూక్లియోఫైల్స్, another one is neutral nucleophiles. So here the nucleophiles are classified into two types. One is charged nucleophiles, another one is neutral nucleophiles. Let us discuss that is charged nucleophiles and neutral nucleophiles. So actually first of all, charged nucleophiles means high electron density species. These are having high electron density. Charge untavi vitiki. So that is generally negatively charged species acts as a nucleophiles. So that is for example Cl minus, Br minus, I minus, Cn minus, OH minus, next that is R minus. All these are but charged nucleophiles. Negative charge ఉంది, ఎలక్ట్రాన్ డెన్సిటీ ఎక్కువ ఉంది. ఇది ఎక్కడ అటాక్ అవుతుంది, ఎక్కడైతే ఎలక్ట్రాన్ డెన్సిటీ తక్కువ ఉందో అక్కడ అటాక్ అవుతుంది. వాటిని ఏమంటాము, న్యూక్లియోఫైల్స్ అంటాము. న్యూక్లియోఫైల్గా యాక్ట్ చేయాలంటే కంపల్సరీగా దాని దగ్గర 8 ఎలక్ట్రాన్స్ ఉండాలి. 8 ఎలక్ట్రాన్స్తో పాటు లోన్ పేర్ ఉంటే మాత్రమే అది న్యూక్లియోఫైల్గా యాక్ట్ చేస్తుంది. నెక్స్ట్ న్యూట్రల్ న్యూక్లియోఫైల్స్. This neutral nucleophiles, example, suppose you take NH3, 5th group hydrides. Here if you observe this NH3, 3 to the 6, 3 6, 6 plus 2, 8 ఎలక్ట్రాన్లు ఉన్నాయి. ఆక్టెట్ ఎలక్ట్రానిక్ కాన్ఫిగరేషన్ ఉంది, దాంతోపాటు లోన్ పేరు ఉంది. NH3 అనేది న్యూక్లియోఫైల్గా యాక్ట్ చేస్తుంది. అదేవిధంగా PH3, అదేవిధంగా ASH3, అదేవిధంగా H2O. Similarly this is H2O, H2S, H2SE. Next అదేవిధంగా ROH, alcohols. Next RCOOH, this one also acts as a nucleophiles. All these acts as a nucleophiles. So here once again in your alkylhalides and arylhalides, the important topic is the nucleophilic substitution reactions. So here we need some basic terms that we are going to discuss. That we are discussing, that is nucleophile. First of all, the species which attacks where the electron density is less, that is called nucleophile. Nucleophile, it is a electron rich species. Here it is electron rich species. It is an active electron pair donor. Now this one, it is acts as a Lewis base. Nucleophiles can be classified into two types, that is charged nucleophiles and neutral nucleophiles. charged nucleophiles ICl minus, Br minus, I minus, Cn minus, OH minus, R minus, etc. Neutral nucleophiles NH3, PH3, ASH3, H2O, H2S, H2SE, all these are. న్యూక్లియోఫైల్ గా యాక్ట్ చేయాలి అంటే కంపల్సరీగా 8 ఎలక్ట్రాన్స్ ఉండాలి. 8 ఎలక్ట్రాన్స్తో పాటు లోన్ పేర్ ఉంటే, సెంట్రల్ ఆటమ్ మీద 8 ఎలక్ట్రాన్స్తో పాటు లోన్ పేర్ ఉంటే అది న్యూక్లియోఫైల్గా యాక్ట్ చేస్తుంది. ఒక ఎగ్జాంపుల్, ఇంపార్టెంట్ ఎగ్జాంపుల్, దట్ ఈస్ నోట్. In the note, suppose if you take CH2, this CH2, this is nothing but carbenes. అందరికి ఒకటి ఏంటంటే ఇక్కడ కార్బీన్ అనేది లోన్ పేరు ఉంది కదా, ఇది న్యూక్లియోఫైల్ లాగా యాక్ట్ చేస్తుందంటే నెవర్, కార్బీన్స్ నెవర్ యాక్ట్స్ యాజ్ ఏ న్యూక్లియోఫైల్స్. వై? బికాస్ ఇఫ్ యూ అబ్జర్వ్ దిస్ వన్, carbene, this is hydrogen, and it is lone pair. So total here lone pair is present, but it is an electron deficient species. Ikkada 1, 2 bonds, 2 to the 4, 4 plus 2, 6 electrons present. Therefore, this never acts as a nucleophile, this one acts as a electrophile. Carbenes acts as a electrophiles, carbenes never acts as a nucleophiles even though it is having lone pair of electrons. So this is regarding nucleophiles. Nucleophilicity means donation of electron pair to the carbon atom. Donation of electron pair to the carbon atom is nothing but nucleophilicity. The reactivity of nucleophile is also called, nucleophilicity. Here donation of electron pair to the carbon atom or the reactivity of nucleophile is also called nucleophilicity. Here we need one more definition, so that is basicity. So what is the difference between basicity and nucleophilicity? Here basicity is nothing but donation of electron pair to H plus or hydrogen atom. Donation of electron pair to H plus, that is called basicity. Here also donation of electron pair, there also donation of electron pair. Here donation of electron pair to the carbon atom, there donation of electron pair to the H plus. That is the difference between nucleophilicity and basicity. Here nucleophilicity, the reactivity of nucleophile or donation of electron pair to the carbon atom. So this nucleophilicity, it depends on so many factors. So here from left to right, let us discuss which factors affect the nucleophilicity. From left to right in a period, nucleophilicity decreases. Why? Because the electronegativity increases, therefore nucleophilicity decreases. See here, for example, this is CH3 minus. Next, this is carbon is a 4th group element, and NH2 minus, this is 5th group element, and OH minus, this is 6th group element nucleophile, and F minus, this is 7th group element nucleophile. From left to right, electronegativity increases, therefore tendency to donate lone pair decreases, therefore nucleophilicity decreases. CH3 minus is greater than NH2 minus is greater than OH minus is greater than F minus. That means CH3 minus, it is having greater nucleophilicity when compared to F minus. Next, from top to bottom in a group, nucleophilicity increases. So here in this one, we have two factors. One is nucleophilicity increases in polar protic solvents. Generally we are taking polar protic solvents. In polar protic solvents, nucleophilicity increases. That means F minus is less than, Cl minus is less than, Br minus is less than I minus. From top to bottom in a group, nucleophilicity increases in polar protic solvents, that is F minus is less than, Cl minus is less than, Br minus is less than I minus. Similarly, here if we change the solvent, this is a polar protic solvent. So, if we change the solvent into that is polar aprotic solvent, from top to bottom nucleophilicity increases, whereas here nucleophilicity increases, here nucleophilicity decreases. Decreases in what? In polar aprotic solvents. That means, let us take example DMSO. DMSO is nothing but dimethyl sulfoxide. Dimethyl sulfoxide is a solvent. In this one, if you observe, that is F minus is greater than Cl minus is greater than Br minus is greater than I minus. In polar protic solvent, the nucleophilicity of I minus is greater. In polar aprotic solvent, the nucleophilicity of F minus is greater. Actually, here we need one more point here. So, that is regarding solvents. Solvents are mainly two types, that is polar solvents and non-polar solvents. Here polar solvents are, that means if mu is not equal to 0, that is a polar solvent. Non-polar solvent means here mu equal to 0, that means polarity is 0. Example, here in this one we have example, that is CCl4 and CS2, similarly benzene, etc. These are non-polar solvents. In polar solvents, again these are classified into two types. Polar protic solvents, another one is polar aprotic solvents. In polar protic solvents, that is polar protic solvent gives protons, example water, ethyl alcohol. So, these are polar protic solvents. Polar aprotic solvents, these having polarity, but they do not give H plus ion. These are polar aprotic solvents. Nucleophilicity is nothing but donation of electron pair to the carbon atom, or the reactivity of nucleophile is called nucleophilicity. Basicity is nothing but donation of electron pair to H plus. Here nucleophilicity, it depends on so many factors. From left to right in a period, nucleophilicity, decreases. CH3 minus is greater than NH2 minus is greater than OH minus is greater than F minus. From top to bottom in a group, nucleophilicity increases in polar protic solvents. From top to bottom in a group, nucleophilicity decreases in polar aprotic solvents. So, in polar aprotic solvents, example DMSO, that is F minus is greater than, Cl minus is greater than, Br minus is greater than I minus. Actually, before going to discuss the nucleophil, that is solvents, nucleophilicity, now we need some clarity regarding solvents. Solvents are mainly classified into two types, that is polar solvents and non-polar solvents. Polar solvents, that is mu is not equal to 0, whereas non-polar solvent mu equal to 0. Here example CCl4, CS2, benzene. In polar solvent we have two types, that is polar protic solvents and one is polar aprotic solvents. Polar protic solvent that gives H plus ions, whereas polar aprotic means do not gives H plus. In polar protic solvents, that is H2O, ethyl alcohol, acetic acid, these are polar protic solvents. Polar aprotic solvents DMSO, DMF and DMA, these are polar aprotic solvents. Polar protic solvents. Examples: H2O, ethyl alcohol, not only ethyl alcohols, and carboxylic acid CH3 C double bond OH. Here H is present, here H is present, here also H is present. These are polar protic solvents. Polar aprotic solvents, examples: acetone. Acetone is nothing but CH3 C double bond CH3. This is a acetone. Similarly DMSO, this is nothing but dimethyl sulfoxide. This dimethyl sulfoxide is CH3 S double bond O CH3. So, here the difference between acetone and DMSO, here acetone, here carbon is present, in DMSO sulfur is present. That is the difference between acetone and DMSO. So, here acetone and DMSO both are polar aprotic solvents, they do not give H plus ion. Here why? Because H plus is not attached to oxygen, here H plus is attached to carbon. This is DMSO, this is acetone. Similarly, DMF is nothing but dimethyl formamide. This dimethyl formamide is HC double bond O NCH3CH3. This is dimethyl formamide, this is a formamide, this is a dimethyl formamide. Next, DMA, this dimethyl acetamide. Dimethyl acetamide is nothing but CH3, C double bond O, N, CH3, CH3. This is a dimethyl acetamide. Acetone, DMSO, DMF, DMA. Now, everybody is having doubt that is, sir, why we are discussing regarding solvents. Actually, these solvents also decides the reaction either SN1 or SN2. Actually, this polar aprotic solvent favors SN1 reaction, polar aprotic solvent favors SN2 reaction. So, this is polar aprotic solvent, this is polar aprotic solvent, this is acetone, DMSO, DMF and DMA. So, after this one, so this is regarding, this is solvents. So, we are discussing that is regarding, nucleophilicity. In nucleophilicity, so that is, so far we are discussing 2 points. One point is from left to right in a period, nucleophilicity decreases from top to bottom in a group, nucleophilicity increases in polar aprotic solvents and nucleophilicity decreases in polar aprotic solvents. That means these solvents also affects the nucleophilicity of nucleophile. So, after this one, next one is charged nucleophiles are stronger than uncharged its parent nucleophile. If we take example, suppose a OH minus, the nucleophilicity of OH minus is greater than H2O. Similarly, NH2 minus, the nucleophilicity of NH2 minus is greater than NH3. Here NH2 minus is formed from NH3, OH minus is formed from H2O. Similarly, so that is similarly, if you take RO minus, the nucleophilicity is greater than ROH. If you take SH minus is greater than H2S. Similarly, RSH is less than RS minus. This is regarding nucleophilicity. The nucleophilicity of charged nucleophiles is greater than, stronger than, that is stronger than uncharged its parent nucleophile. OH minus is greater than H2O, NH2 minus is greater than NH3, RO minus is greater than ROH, SH minus is greater than H2S, RSH is RSH is less than RS minus. Similarly, as the bulkiness increases, nucleophilicity decreases. Suppose if you take this is CH3, CH2O minus, CH3, CH3O minus. This is ethoxide ion, this is tertiary butoxide ion. This ethoxide ion and tertiary butoxide ion, due to this large group, due to this bulky group, here it does not easily attacks on carbon. Therefore, here it is a poor nucleophile. This is a poor nucleophile. And whereas it is a smaller, it easily attacks on carbon. Therefore, this is a stronger nucleophile. That means the nucleophilicity of ethoxide ion is greater than what? Tertiary butoxide ion. This is called tertiary butoxide, this is called ethoxide ion. here it is a strong base, and here it is a weak base. Weak base, but it is a stronger nucleophile. It is a strong base, it is a poor nucleophile. Due to that bulkiness, it does not easily attacks on carbon, therefore the nucleophilicity of this one is less than here ethoxide, right. Next one, in this one, see here in some cases that is nucleophilic center is same, but nucleophilic group is different. That means donor atoms are same, but donating groups are different. Here if nucleophilic center is same but nucleophilic group is different, that means donor atoms are same but the donating groups are different, then nucleophilicity is parallel to basicity. Donor atoms are same but the donating groups are different, then the nucleophilicity is parallel to basicity. Donor atoms same ఉంటాయి, donating groups different గా ఉంటాయి. అంటే ఏంటి? ఎగ్జాంపుల్ తీసుకుందాం. సపోజ్ CH3 C double bond O minus, CH3 CH2 O minus. Here in this one, donating group donor atom is oxygen. This is a donor atom, this is also donor atom. But the donating group means this is totally, it is called donating group. Here also this total group is called donating group. This is a donor atom, this is also donor atom, but the donating group is different. Then what happens? Nucleophilicity is parallel to basicity. So nucleophilicity is parallel to basicity. How we decide? So first of all, convert this one into acid. This is formed from acetic acid, CH3COOH. This is formed from ethyl alcohol, CH3CH2OH. This is carboxylic acid, acetic acid. The acidic nature of acetic acid is greater than ethyl alcohol. This is a strong acid, but relatively when compared to this one, acetic acid is a strong acid and it is a weak acid. Strong acid will have weak conjugate base. This is a weak acid will have strong conjugate base. Therefore, here what beta? Here this is nucleophilicity is parallel to basicity. Nucleophilicity is parallel to basicity means this is a strong conjugate base, therefore it is a strong nucleophile. That means the nucleophilicity of ethoxide ion is greater than acetate ion. So nucleophilicity here we have so far we have discussed, that is from left to right nucleophilicity decreases, from top to bottom nucleophilicity increases in polar protic solvents, decreases, and also we have discussed regarding solvents, so what is polar solvent, what is non-polar solvent, polar protic solvent, what is polar protic and what is polar aprotic. After that one, next charged nucleophiles are stronger than its uncharged its parent nucleophile, OH minus and H2O. As the bulkiness increases, nucleophilicity decreases. If nucleophilic center is same, but the nucleophilic group is different. That means donor atoms are same, but the donating groups are different. Then nucleophilicity is parallel to basicity. This is acetate and this is ethoxide ion. Now we are comparing the nucleophilicity. So that means this is a stronger nucleophile. This is a nucleophilicity. We are comparing the nucleophilicity of acetate ion and ethoxide ion. So how we compare? So first of all, convert into acid. This is acetate is formed from acetic acid. Ethoxide is formed from ethyl alcohol. This is a strong acid, that is a weak acid. Strong acid will have weak conjugate base. Weak acid will have strong conjugate base. This is therefore the nucleophilicity of ethoxide ion is greater than acetate ion. We are completed regarding nucleophilicity and basicity. Now we have one more term, that is leaving group ability. This is a leaving group. This is also called nucleophugacity or nucleophugality. Nucleophugality or nucleophugality both are same regarding a leaving group. So leaving group here, leaving group ability is inversely proportional to basicity. Basicity. Basicity is inversely proportional to leaving group ability. So weak base acts as a good leaving group. So here that means we need acidic nature. Here we need to learn regarding acidic nature. That is leaving group ability is inversely proportional to basicity. Strong base acts as a poor leaving group, weak base acts as a good leaving group. See here for example, if we observe that is CH3 CH2O minus, CH3 CH2O minus and CH3 COO minus, leaving group ability. So leaving group ability, it is formed from, this is formed from ethyl alcohol CH3CH2OH, this is formed from acetic acid CH3COOH. The acidic nature, that is acetic acid, strong acid, acidic nature of acetic acid is greater than ethyl alcohol. Strong acid will have weak conjugate base is a good leaving group. Therefore, that is leaving group ability that is ethoxide ion is less than acetate ion. Suppose if you take in groups from top to bottom, leaving group ability increases. Sir, how leaving group ability increases? Let us discuss. For example, F minus, Cl minus, Br minus, I minus. So first of all, convert into its acid HF, HCl, HBr, Hi. Acidic nature in any group hydrides from top to bottom, electronegativity decreases and size increases, size of the atom increases, bond length increases and bond energy decreases. Therefore, acidic nature increases. From top to bottom, acidic nature increases. Acidic nature increases. That means HF is less than, HCl is less than, HBr is less than Hi. Hi is a strong acid. Strong acid will have weak conjugate base. That means this is a weak acid. This weak acid will have strong conjugate base. Strong acid will have weak conjugate base. Let us take that is a basic F minus, Cl minus, Br minus, I minus. This is strong acid kabatti the weak conjugate base. It is weak acid kabatti strong conjugate base. Basic nature gurinchi తీసుకున్నప్పుడు basicity తీసుకున్నప్పుడు F minus is greater than Cl minus is greater than, Br minus is greater than I minus. Next, this is basicity, weak base acts as a good leaving group. Therefore, leaving group ability, that is F minus is less than, Cl minus is less than, Br minus is less than I minus. So, F minus is less than, Cl minus is less than, Br minus is less than I minus. Leaving group ability from top to bottom increases. I minus is a good leaving group, F minus is a poor leaving group. Similarly, suppose let us discuss regarding some good leaving groups, regarding some good leaving groups. The good leaving groups are, suppose if you take that is diazonium salt N2X minus, this is a good leaving group. After the elimination of N2 plus, that becomes more stable N triple bond N. Similarly, suppose if you take this one, this is a tosylate, this is called tosylate. Sir, what is tosylate? Tosylate is nothing but paratoluene sulfonate. Paratoluene sulfonate is, this is paratoluene, this is a toluene, paratoluene S double bond O, O minus. This is a paratoluene sulfonate. Here, this is also good leaving group, this is a tosylate. Similarly, triflate. Triflate acts as a good leaving group, that is CF3 S double bond O, O minus. This is a triflate. Triflate is a good leaving group. This is CF3 SO3 minus. This is a paratoluene sulfonate. This is a tosylate and this is a triflate. Similarly, brocylate. brosylate. So this brosylate, in this brosylate, that is para-bromo sulfonate, this para-bromo sulfonate, this is also good leaving group. These are some good leaving groups: tosylate, triflate and brosylate and N2 plus X minus. This is regarding leaving group ability. Leaving group ability is nothing but nucleophugacity. Leaving group ability is inversely proportional to basicity. That means weak base acts as a good leaving group. Here compared, that is ethoxide and acetate ion, and in groups from top to bottom leaving group ability increases. So how it increases we are discussed here. And some good leaving groups. So why these acts as a good leaving groups means these are formed from very strong acids. So strong acids will have weak conjugate base. Weak conjugate base acts as a good leaving groups. Now we are going to discuss, that is nucleophilic substitution reactions. So far we are completed, that is basic terms that required in nucleophilic substitution reactions. So now let us discuss regarding nucleophilic substitution reactions. These nucleophilic substitution reactions can be classified into two types. These can be classified into two types: aliphatic nucleophilic substitution reactions, and one more is aromatic nucleophilic substitution reactions. One is aliphatic nucleophilic substitution reaction, another one is aromatic nucleophilic substitution reaction. That means nucleophilic substitution reactions takes place at in aliphatic carbons, that is that one takes place in aromatic carbons. These aliphatic nucleophilic substitution reactions, again it is classified into, mainly these are classified into SN2 reaction and one more is SN1 reaction. Here aromatic nucleophilic substitution reactions, these can be classified into two types, that is addition elimination reactions, addition elimination reactions. Another one is elimination addition reactions, elimination addition reactions, elimination addition reactions, addition elimination reactions and elimination addition reactions. Here nucleophilic substitution reactions are two types: aliphatic nucleophilic substitution reactions and aromatic nucleophilic substitution reactions. This is SN2 reaction. These can be classified in two types, that is SN2 and SN1. Aromatic nucleophilic substitution reactions again classified into two types, that is addition elimination reactions and elimination addition reactions. Now we are continuing, that is now we are going to concentrate, that is aliphatic nucleophilic substitution reaction. First of all, now we are going to discuss, that is SN2 reactions. SN2 reaction, where it happens. So here in SN2 reaction, not only in alkyl halides, SN2 reaction and SN1 reaction takes place in different types of compounds. Alcohols, in alcohols also possible, in alkyl halides, in ethers. So many compounds, these nucleophilic substitution reactions takes place, and all these reactions are very important in all entrance examination point of view. Every year 1-2 questions are coming in any exam, 1-2 questions are coming from this topic. It is very and difficult topic. So we can't differentiate what is SN1 and what is SN2. So students are facing that problem. చాలా మంది స్టూడెంట్స్ ఏంటంటే చాలా మంది ఫేస్ చేస్తారు SN1 SN2కి డిఫరెన్షియేట్ చేయడం అనేది, కానీ చాలా సింపుల్. సో దిస్ ఈజ్ ఫస్ట్ ఆఫ్ ఆల్ లెట్ us discuss, that is regarding SN2 reactions. This is a bimolecular nucleophilic substitution, bimolecular nucleophilic substitution reaction. This is 2 means, here this is SN2, 2 means bimolecular nucleophilic substitution reactions. This is SN2 reaction. Let us discuss regarding SN2 reactions గురించి మనము డిస్కస్ చేద్దాం. SN2 reactions ఎక్కడ జరుగుతాయి, ఎలా జరుగుతాయి. మనం ఒక alkyl halide తీసుకుందాం. See here, this is a C, this is CH3, here it is having H, here it is having deuterium, it is having deuterium, and here it is I. Here this is CH3, C, H, D and I. If you observe this compound, in this compound, this is a which carbon? This is a chiral carbon. Chiral carbon means the carbon which is attached with 4 different groups. ఇది chiral carbon అంటే ఒక కార్బన్ అనేది 4 డిఫరెంట్ గ్రూపులను కలిగి ఉంటే దాన్ని కైరల్ కార్బన్ అంటాం. ఈ కైరల్ కార్బన్లో దీన్ని ఏం చేస్తున్నామంటే మనము aqueous 𝗂𝗧తో రియాక్ట్ చేస్తున్నాం. aqueous 𝗂𝗧తో రియాక్ట్ చేస్తున్నప్పుడు I- అనేది OH- తో రిప్లేస్ అవుతుంది. So here we get this compound, this is CH3, here it is OH, this is here it is deuterium, and here it is this is H. Now let us discuss that mechanism, what happens in this one, what happens in this one. Here this is a CH3, this is here it is H, this is a deuterium, here it is a deuterium and this is I. So what is this indication? These two normal lines indicates along the plane, and this is the thick line indicates above the plane and the broken line indicates below the plane. Why? Because this is sp3 and tetrahedral molecule. Now the nucleophile is OH-, here OH-. This OH- is attacking from the so opposite of the leaving group. OH- is attacking from the back side of the leaving group. This I- is eliminated. Actually this is a slow step, and it is a slow step is always rate determining step. So what happens? Actually this reaction proceeds through transition state. Actually this reaction completed within one step. And here what happens here? This is CH3, here it is H, this is a deuterium, above the plane, and here this bond undergoes cleavage, this is I and this is OH, this is minus and this is also minus, and here this is indicating it is a transition state, this is a transition state. This proceeds through a transition state. And what happens? This is only one step, but here we are indicating how bond is undergoing cleavage and how new bond is forming. And what happens here? In this one, this is CH3. Here it is. In this one, this is we have this is deuterium. It is above the plane. This is deuterium. It is above the plane, and this is hydrogen below the plane. Here it is OH. So totally vertical, that is totally inverted the molecule. That means here inversion takes place. I- ముందు నుండి వెళ్ళిపోతే OH- బ్యాక్ నుంచి అటాక్ అయిపోయింది. బ్యాక్ నుంచి అటాక్ అయిందంటే జస్ట్ లైక్ ఇట్ ఈజ్ ఇన్వర్షన్, జస్ట్ లైక్ అంబరెలా టైప్. సో ఇక్కడ మనం అబ్జర్వ్ చేసినప్పుడు ఇది ఇన్వర్షనా కాదా అనేది దీని కాన్ఫిగరేషన్ బట్టి చెప్పొచ్చు. ఎలా అంటే ఇది RA-SR తీసుకోవచ్చు. RA-SR తీసుకున్నప్పుడు దిస్ ఇస్ 1, దిస్ ఇస్ 2, దిస్ ఇస్ 3, this is 4. Here 1, 2, 3 anti-clockwise direction, or otherwise we can convert this one into Fischer, that is CH3. Here this I and this is deuterium, this is H. So here this is above the plane, this is indicated right side, this is indicated left side, this is CH3 and I. Here this one goes first priority, this one goes second priority, this one goes third priority, this one goes fourth priority. 1, 2, 3 clockwise direction. Clockwise direction means here it is S. Why? Because the fourth priority is present in horizontal. If fourth priority is present in vertical, that is clockwise direction is R, anti-clockwise direction is S. This is S configuration. The compound configuration is S. If you observe this one, now convert this one into Fischer. This is here it is CH3, bottom is OH, now deuterium, and this is H. Here it is 1, this is 2, this one goes to second priority, this one goes to third priority, this one goes to fourth priority. Now observe the 1, 2, 3 groups of these are present. 1, 2, 3, that is 1, 2, 3 it is anti-clockwise direction, that means this is R configuration. Here S configuration is converted into R configuration. Totally inversion takes place. This is called Walden inversion. This is called Walden inversion. Walden inversion takes place. In SN2 reaction, the nucleophile is attacking from the back side. Therefore, here in SN2 reaction, Walden inversion takes place. Here S is converted into R. Suppose if reactant, if it is having R, then R is converted into S. This is a Walden inversion. This reaction takes place through a transition state, and this reaction completed in one step, and here this reaction this completed in one step, therefore these are called concerted reaction. Concerted reactions. Concerted reaction means the reactions which are completed within one step, that is called concerted reaction. So here in this bimolecular reaction, now let us discuss that is regarding rate. So rate is directly proportional to, rate depends on where? Rate depends in slow step, always depends on slow step. Slow step, it is a rate determining step. This is a, in slow step, if you observe, so two molecules are participating, one is alkyl halide, another one is nucleophile. Rate is directly proportional to concentration of alkyl halide and concentration of that is nucleophile, concentration of nucleophile. So in this one, if you write here, rate is directly proportional to, that is CH3 CHDI, and here concentration of OH minus. That means rate equal to K into, that is CH3 CHDI, and it is OH minus. Here with respect to this one, this is a first order alkyl halide. With respect to this one, this is also first order. With respect to nucleophile, first order. With respect to alkyl halide, first order. Overall order, it is a second order reaction. It is a second order reaction. Here second order reaction, that is alkyl halide and nucleophile. So that means what is the meaning of second order? What is the meaning of rate? Suppose if we increase the concentration of nucleophile, rate also increases. If we increase the concentration of alkyl halide, rate also increases. Suppose if the concentration of this one increased by 2 folds, if the concentration of nucleophile increases by 2 folds, then what happens? Rate increases by 4 times. Rate increases by how many times? 4 times. Suppose if this is increased by 3 times, if the concentration of nucleophile is decreased by half, then what happens? This is increased by 3 times, this is decreased by half, therefore the rate, total overall rate is 3 by 2, that is nothing but 1.5 times increases. Here that means total, that is SN2 reaction depends on the concentration of alkyl halide as well as concentration of nucleophile. Therefore this is called bimolecular and it is a second order reaction. Now let us discuss that is energetic diagram of SN2 reaction. If we draw the graph, that is free energy versus that is reaction coordinate or progress of the reaction, both are same. So here in this one, this reaction takes place through a transition state. Here we have only one peak. This is a nucleophiles, this is a nucleophile and alkyl halides. This is the energy of nucleophile and alkyl halide, and this is a transition state, and this is a product ROH plus X minus. This is a leaving group and this is a alcohol. This is energetic diagram. So after energetic diagram, now then let us discuss that is which factors affecting on the rate of SN2 reaction. What are the factors which affects the rate of SN2 reaction? First of all, that is structure of alkyl halide. How the structures of alkyl halide affects the rate of SN2 reaction? Here, so in SN2 reaction, nucleophile is attacking from the back side of the leaving group. Here, if you take tertiary, here this is CH3, here it is CH3, here it is CH3, here this is I. Next here, this is CH3, CH, this is CH3, this is I. And here, this is CH3, this is CH3, and here this is a tertiary alkyl halide, this is secondary alkyl halide. In secondary alkyl halide, this is hydrogen, I am writing like this. And here we have that is primary alkyl halide, this is CH3, here it is H, this is H, and this is I. Similarly, take that is methyl halide or methyl iodide. Here we have 4 compounds. This is tertiary, this is secondary, this is a primary, and this is a methyl iodide. Methyl iodide. Now, here nucleophile is approaching from the back side of the leaving group. Here also nucleophile is approaching from the back side of the leaving group. Here also nucleophile is approaching from the back side of the leaving group. Here also nucleophile is approaching from the back side of the leaving group. So, where it easily attacks. Whereas if you observe this one, this is a CH3, this is a CH3, this is a CH3. These 3 are larger groups. These 3 larger groups hinders the attacking of nucleophile and carbon atom. If we observe this one, this is hydrogen smaller, smaller, smaller. All these groups are, all hydrogens are smaller. Therefore, here easily nucleophile attacks from the back side of the leaving group. If we observe these 2, this is tertiary and this is methyl halide. Here bulkiness is more, steric index is more, here steric index is less. Here nucleophile easily approaches from the back side of the leaving group. That means the reactivity of methyl iodide is greater than ethyl iodide, that is primary, and ethyl iodide, this is a isopropyl iodide and this is a tertiary butyl iodide. That means in SN2 reaction, we have to remember one point, nucleophile is approaching from the back side of the leaving group. న్యూక్లియోఫైల్ అనేది బ్యాక్ సైడ్ నుండి అటాక్ అవుతుంది. బ్యాక్ సైడ్ నుండి అటాక్ అవుతుందంటే దాని మీద గ్రూప్స్ అనేది చిన్నగా ఉండాలి. ఒకవేళ పెద్ద గ్రూప్స్ అయితే ఈ పెద్ద గ్రూప్స్ ఏం చేస్తాయంటే న్యూక్లియోఫైల్ అటాక్ కాకుండా కాపాడతాయి. ఇప్పుడు చూడండి ఇక్కడ టెర్షియరీ తీసుకున్నప్పుడు మిథైల్ 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 3 గ్రూప్స్ మిథైల్ వచ్చాయి కాబట్టి ఇది అంత ఈజీగా అటాక్ కాదు. కాబట్టి దీని రియాక్టివిటీ చూడండి, హైడ్రోజన్ హైడ్రోజన్, ఇక్కడ CH3H, ఇక్కడ CH3H, ఇక్కడ 2 CH3 ఒక H ఉంది. ఇక్కడ స్టీరిక్ ఇండెన్స్ దీంతో పోల్చుకుంటే తక్కువ, ఇక్కడ ఇంకా తక్కువ, ఇక్కడ ఇంకా తక్కువ, ఇక్కడ స్టీరిక్ ఇండెన్సే లేదు, ఈజీగా బ్యాక్ సైడ్ నుంచి అటాక్ అవుతుంది. కాబట్టి రియాక్టివిటీ టెర్షియరీ ఈజ్ లెస్ దాన్, సెకండరీ ఈజ్ లెస్ దాన్ ప్రైమరీ. ద రియాక్టివిటీ ఆర్డర్ ఈజ్ టెర్షియరీ ఆల్కైల్ హాలైడ్ ఈజ్ లెస్ దాన్ సెకండరీ ఆల్కైల్ హాలైడ్, సెకండరీ ఆల్కైల్ హాలైడ్ ఈజ్ లెస్ దాన్ ప్రైమరీ ఆల్కైల్ హాలైడ్, primary alkyl halide is less than methyl halide. That means this is reactivity towards SN2 reaction. In SN2 reaction, primary alkyl halide and methyl halides undergoes easily SN2 reaction. అనగా అంటే ఏంటి, ఫర్ ఎగ్జాంపుల్ టెరిషరీ సెకండరీ ప్రైమరీ ఇచ్చేస్తుంటే సాధారణంగా 99% ప్రైమరీ ఇవ్వగానే SN2 రియాక్షన్ అని పెట్టవచ్చు. టెరిషరీ అనేది చాలా చాలా తక్కువ, అసలు టెరిషరీ అనేది SN2 రియాక్షన్లో పార్టిసిపేట్ కాదు. SN2 రియాక్షన్లో పార్టిసిపేట్ అయ్యేది ప్రైమరీ అండ్ మిథైల్. మంది డౌట్ వస్తుంది సెకండరీ పరిస్థితి ఏంటి. సెకండరీ అనేది SN2 రియాక్షన్ పార్టిసిపేట్ కావచ్చు, SN1 రియాక్షన్లో పార్టిసిపేట్ కావచ్చు. హౌ వీ కెన్ డిసైడ్ దట్ ఆఫ్టర్ కంప్లీషన్ ఆఫ్ దట్ ఈస్ SN1 ఐ విల్ ఎక్స్ప్లెయిన్. ఓకే, ఇక్కడ ప్రైమరీ అనగానే కళ్ళు మూసుకొని చెప్పొచ్చు SN2 రియాక్షన్. టెరిషరీ అంటే SN2 రియాక్షన్లో పార్టిసిపేట్ కాదు. సెకండరీ అనేది కూడా SN2లో పార్టిసిపేట్ అవుతుంది, SN1లో పార్టిసిపేట్ అవుతుంది. దాన్ని ఎలా డిఫరెన్షియేట్ చేయొచ్చు అంటే మనం సాల్వెంట్ను మరియు న్యూక్లియోఫైల్ యొక్క కాన్సన్ట్రేషన్ బట్టి మనము సెకండరీ అనేది దట్ ఈస్ సెకండరీ ఆల్కైల్ అనేది SN2లో పార్టిసిపేట్ అవుతుందా, SN1లో పార్టిసిపేట్ అవుతుందా అనేది చెప్పవచ్చు. SN2 రియాక్షన్లో ఫ్యాక్టర్స్ గురించి మనం డిస్కస్ చేస్తున్నాము. ఫస్ట్ ఆఫ్ ఆల్ స్ట్రక్చర్ ఆఫ్ ఆల్కైల్ హాలైడ్ అయిపోయింది. స్ట్రక్చర్ ఆఫ్ ఆల్కైల్ హాలైడ్లో ప్రైమరీ ఈజ్ గ్రేటర్ దాన్, సెకండరీ ఈజ్ గ్రేటర్ దాన్ టెర్షరీ. దాని తర్వాత the next second one is that is regarding nucleophile. How nucleophile affects the rate of SN2 reaction. Here in this one, nucleophile actually SN2 reaction rate is directly proportional to concentration of alkyl halide and concentration of nucleophile. That means rate depends on nucleophile concentration also. That means here if we take strong nucleophiles and also high concentration of nucleophiles. High concentration of nucleophiles and strong nucleophiles favors SN2 reaction. Here already we have discussed that is weak nucleophile and strong nucleophile. What is weak nucleophile and what is strong nucleophile? Nucleophilicity regarding nucleophilicity. Simply suppose negative charged species are given, for example OH minus, Cl minus or Br minus or I minus. If these are given, then definitely this is a SN2 reaction. SN2 reaction depends on the concentration of the nucleophile, therefore strong nucleophiles and high concentration of nucleophile favors SN2 reaction. Next, after nucleophiles. Third one is, so how solvent affects the rate of SN2 reaction. Here already we have discussed that solvents are two types, that is polar solvents and non-polar solvents. And polar solvents are again two types, that is polar aprotic solvents and polar aprotic solvents. Here polar aprotic solvents favors SN2 reaction. Polar aprotic solvents favors SN2 reaction. That means in any reaction, if acetone is given, CH3 double bond O CH3, acetone is given, or DMSO is given, DMSO is nothing but dimethyl sulfoxide, CH3 S double bond O CH3, dimethyl sulfoxide, DMSO is given, or otherwise DMF is given, DMF dimethyl formamide, HC double bond O N CH3, DMF is given, or otherwise DMA given, DMA dimethyl acetamide, that is CH3 C double bond O N CH3 dimethyl acetamide. If these are given, definitely this favors which reaction? SN2 reaction. So by using nucleophile, by using solvent, we can decide is it SN1 reaction or SN2 reaction. That is acetone, DMSO, DMF and DMA, generally these favors SN2 reactions. This is nucleophile and that is regarding solvent. The first factor is structure of alkyl halide, and the second factor is regarding nucleophile, third factor is solvent, and next fourth factor, that is fourth factor. So what is that fourth factor? Regarding leaving group. Good leaving group favors both SN1 as well as SN2. That means leaving groups, good leaving groups favors both SN1 as well as SN2 reactions. See here. Now then fifth factor, that is low temperature favors. That means low temperature and moderate temperature, medium temperature favors SN2 reaction, and high temperature favors SN2 as well as SN1 reaction. High temperature favors, that is elimination reaction. High temperature favors elimination reactions and low temperature favors SN2 as well as SN1 reaction. And next one, this is sixth one. Sir, which factors? And here this one, in this reaction nucleophile attacks from the backside of the leaving group. Therefore, here steric hindrance required less. And here one more point here, electron withdrawing groups at beta carbon, that means it is attached to alpha carbon, favors SN2 reaction. Why? Because electron withdrawing groups stabilizes the transition state. Therefore, electron withdrawing groups at beta carbon increases the, or it favors the SN2 reaction. For example, CH3 C double bond O CH2Cl, CH3 C double bond O CH2Cl. This is alpha with respect to Cl, this is alpha, and this is a C double bond O, this is a electron withdrawing group. This electron withdrawing group stabilizes the transition state, therefore it favors SN2 reaction. So, and here one more point here, that is bridged bicyclo compounds. So this one, if you take this example neither undergoes SN2 reaction nor SN1 reaction. Indulo SN2 reaction possible kaadu, SN1 reaction possible kaadu. ఇక్కడ కార్బోకటయాన్ ఫామ్ కాదు, ఇక్కడ స్టీరిక్ హండ్రెన్స్ ఎక్కువగా ఉంది కాబట్టి బ్రిడ్జ్డ్ బైసైక్లో కాంపౌండ్స్లో ఒకవేళ హాలోజన్ ఉంటే అది SN1 రియాక్షన్లో పార్టిసిపేట్ కాదు, SN2 రియాక్షన్లో పార్టిసిపేట్ కాదు. దిస్ ఈజ్ రిగార్డింగ్ SN2 రియాక్షన్స్.